is take 2 on this video. We are going to finish up the related rates problem practice A. We're going to do D, E, and F. To dive right in, D says 2 automobiles start from point A at the same time. Let's get point A at the same time. Where is point A? Point A looks like it's right there, Mr. Lakin. Excellent. One of those automobiles, I don't know why I call them, they're cars. Just call them cars, or oh, I guess they may not be cars. Motor vehicles. Let's call them motor vehicles. One of these motor vehicles travels west at 80 miles per hour. The thing I noticed about this 80 miles an hour, in addition to the travels west, is that this is a rate of change. This is a derivative value. We have one car going west. Here's west, and that's 80 miles an hour. Because this car is in motion, if I was to say, where is this car at? Well, we don't know where the car is at because the car is actually in motion. It's driving still. So while we can say that the car is going 80 miles an hour, its position at any time is kind of unknown. So we'll just say that that's an X. Now the other automobile, motor vehicle, carriage on wheels, travels north at 45 miles per hour. So let's go on and put that here. It says travels north, so we got a car going up and away from the same point A, and it's traveling at 45 miles per hour, and this is also a rate. Now the reason I bring attention to the rate here is, well, I'll tell you in just a second here. Now, because it's traveling, this car is traveling north, or a sedan or a van or whichever it is, maybe a motorcycle, is traveling north at 45 miles an hour. We never know where its actual position is at any time. Because as you're, like, let's say we were calling up the person that's driving this at 45 miles an hour. Hey, where are you at? Oh, well, I'm passing. Because when you're driving, you're like not stopped. You're always in motion. So because this car is always in motion, we can call this value Y. And if these two people were to call each other up, X and Y, they're people now. If we were to call these two people up, we'd say, hey, how far apart are we? Oh my gosh, I don't know, it's always changing. So we could call that Z. The distance between those two is Z. Before I set up an equation here, I want to point out that we don't actually know the values of these just yet. We have to do a little bit of work, just a little tiny drop. So X equals, Y equals, Z equals. But what I'm also taking the time to do at the moment is just fill in all these values. dz dt, we don't know. dz dt is how fast the distance is between them. That's going to be a rate. That's what we're trying to answer in the question. We know Y though. And when I say we know Y, I mean, I don't mean we like know why, but we know why, right? Like not why, but why. Oh, what's he talking about? No one knows. So dy dt, we know what dy dt is. That's 45 miles an hour. Because all of these values, remember, are always rates. And we know what dx dt is. dx dt is 80 miles an hour. You might wonder, well, how did I know that these are all positive values? Because I talked about that in the last video, that sometimes these values are positive for the rates and sometimes these values are negative. Because their distance from A is increasing, because this star, let's put a star on here, because the star, and here's a heart, because the heart is getting farther and farther away from the star, we have a positive, the distance between the star and the heart is increasing, so we have a positive rate. If the heart was to get closer and closer to the star, that means that the heart is closing in on the star. It's getting closer. The distance between them is decreasing, which means that we would have a negative rate. So that was a very poor representation of how you can tell whether you have a positive rate or a negative rate. And if that wasn't clear for you, maybe just rewind back a few, however long I took to explain that, so that way it processes a little bit more for you. I don't have X and Y explicit values there, but what I could do is find them though. It says that the car traveling west, or the automobile traveling west, is 80 miles an hour, and they want to know 3 hours later. So what we can do for X is multiply 80 times 3. Because 80 times 3 gets us 240. That's where that car is, or automobile is, 3 hours later from point A. X is 240 miles away from point A. Similarly, we can multiply Y by that value, And if we do 45 times 3, I believe we get 135 miles. And we need to find z, and we can do that if we do a Pythagorean theorem here. So I'm going to put this off to the side. We're going to need the square root of 240 squared plus 135 squared. And who knows what that is, because I sure don't. Let's see here, square root. Can I do this like this? 240 plus 135. Wow, I can do it like that. But I messed up. 275 miles. 275.363 miles. We'll use three decimal places. What was it? 275.363 miles. 275.363 miles. Again, I got that by doing Pythagorean theorem for the distance that they are away from point A. Now I can set up my equation. I'm going to drop all the colors here and set up the equation. We have a Pythagorean theorem looking triangle, so x squared plus y squared equals z squared. We're going to take their derivatives now with respect to time, so we get 2x dx dt plus 2y dy dt, because I took the derivative of y with respect to t, and that's going to be equal to 2z dz dt. It's kind of fun to say. And let's go and plug in all our values here. We got 2 times 240. 240 miles were driven, and we got 80 for the dx dt. 80. Okay. Plus, we got 2 times 45, 2 times 135 times 45. And then finally, we got 2 times that number times dz dt. Okay, let's see what happens now. I gave up. I have no idea how to, oh shoot, oh man. I'll rewrite all that in, but while I'm rewriting all that in, you should probably just let this video play and try to calculate this on your own. Please go ahead and let this play and try calculating this on your own. Good luck. Use a calculator, because I'm going to use a calculator. I think it's probably safe to say, and I know I haven't recorded it yet, that you should just go ahead and not only try to put this in your calculator, but just fast forward ahead like a minute, because look how long I'm taking here. I got, when I put this all in my calculator, oh, I don't know. That's the sound of me getting my calculator out. What poor quality videos Mr. Lakin makes. 50-50, 5550. We're dividing that by 275.313. And we are going to get some fantastic number. Times 2. Oh gosh, Mr. Lakin, you almost made that mistake. And they would have laughed at you, and you would have cried. And no one likes seeing you cry because it's kind of the ugly crying. 91.8 miles an hour, 04, but 91.8 miles per hour is the distance that is the cars are increasing, that the rate between these cars is increasing. Let's going to go on to E. E says a spherical balloon is inflated so that its radius increases at a rate of 2 over r centimeters per second. How fast is the volume of the balloon increasing when the radius is 4 centimeters? Ooh, we have no idea. But what we can see about the problem, though, is that we have a sphere. And everyone in the world remembers that a sphere is 4/3 pi r to the third. Mr. Goldstein actually came in and actually, he didn't. I lied about that. I was going to make up some story, but it was just going to be silly anyway. Now, we have a spherical balloon. It's inflating. Its radius increases. So let's go and get some numbers on the side here. We have an r value when r is 4. I'm just going to change all the colors here. just so we have that. Okay, so that is radius increases at a rate of 2 over r centimeters. Okay, got it. R is 4. We don't know what drdt is, and yet we kind of do, because it says that drdt is going to be 2 over r. And 2 over r is going to really be 2 over 4, because that's what r is, which is 1/2. Ooh, okay, excellent. So what we need to do is see how fast the volume is, and it doesn't seem like we actually care what the volume is, so we'll just leave that blank, but we do want to know the rate that the volume is changing at. So let's go on and see. Let's take our derivative with respect to time. I'll drop all the colors here, and we got dv dt is equal to, now the 4 over 3 is just going to stay along with the pi. And I'm just going to focus on that r cubed, taking the derivative there. The derivative of r cubed is going to be 3, and then the 3 comes down in front. R squared, our exponent drops by 1. And we just took the derivative of r with respect to time, so we need a dr dt. I also noticed that I got a 3 on bottom and a 3 on top, so those are out of there. Those divide out to 1. So what we have here is that dv dt is equal to, I kind of want to talk like a robot. dv dt is equal to 4 pi r squared times dr dt. And now we can go and plug r in. We get dv dt is equal to 4 pi times 4 squared times 1/2. And once we calculate that, we got our answer. And it looks like it's going to be 32 pi. Units. If I was asking for the units, we're talking about the volume of a sphere, and volume means that we're going to have units cubed, so centimeters cubed per second. So when the radius is 4 centimeters, when the radius of this spherical balloon is 4 centimeters, the rate of the volume is changing at 32 pi cubic centimeters for each second. Pretty good. Let's go and do the last one. Our last one is F. The volume of a cylinder is increasing at the rate of 4 pi cubic centimeters per second. That's a rate. This is a rate. It's a rate. It says right there, it's a rate. Which means that we have a dv dt. dv dt is 4 pi cubic centimeters per second. Which means we may need to know what v is, not sure yet. The radius of the volume of the base is increasing at a rate, okay, radius, we got another radius here. A radius of the base this time is increasing at a rate of 2 centimeters per second. So let's go and do a dr dt for the rate of the radius, and we got 2 centimeters a second. But we'll probably have a radius here at some point, so let's put our r value. How fast is it? How fast is the height of the cylinder changing? What? The height? Oh my gosh, we have another variable here. What am I gonna do with myself? Okay, so let's go and just move this down here. Let's go and put a height in here, and that height, now the doorbell might ring here, so let's see if it will get in the video. dH/dt, we want to know how fast is the height changing, so that's what we're trying to answer. When the volume is 36 pi, okay, volume is 36 pi, got it. And the radius is 3. Ooh, okay. Oh, shoot, they don't give me the height. Okay, well, let's see what we have here. I think you're probably going to remember that the volume of a cylinder is going to be, and I'm going to clean up that, get rid of that G part here in a second, that G beneath F. Volume is equal to pi times r squared, which is the area of the circle for a cylinder, multiplied by the height. Did you remember that? Go on and say it out loud. Just don't interrupt anybody that's near you. Just say out loud, yes, Mr. Lakin, I knew that the volume of a cylinder was 4 pi r squared times h. And I said that wrong. The volume of a cylinder is pi times r squared times h, and I know you knew that. Now, I'm going to go and plug in some stuff just to see what happens here. Let's plug in 36 pi, because that's what the volume is. And we're going to set that equal to pi times that 3 squared. And this isn't the derivative, by the way. This looks like I'm going to actually be able to get h this way. Oh, that's what he's doing. Oh, I see. Okay, so now let's drop the colors except for that blue. So now we have 36 pi equals 9 pi, because 3 squared is 9, and we're multiplying it times pi, times h. And if we divide by that 9 pi, we are going to get that h value, and that h value is going to be 4. So the height is 4. Notice I had to do some extra work to solve for h. Extra work. And I think that idea is new to us of the problems that we've looked at. Extra work for h. Now I drew a cylinder for you, and it's beautiful. And we are going to have the radius changing when we start filling up that cylinder. We're going to have our height changing. Our height. Okay, so that means we can set up our volume equation. We're going to go and take a derivative, but when we take that derivative, we are going to need a product rule with some implicit differentiation. This part is going to be f, this part is going to be s. I'm going to set myself up for success with an f prime times an s plus an s prime times an f. And you're thinking, does he always sing in his videos? No. But do you always sing when you're doing math? Yes. And let's go and take the derivative of f here. We're going to take the derivative of that pi r squared. That pi is going to stay, as pi should always stay. And then the derivative of r squared is going to be 2 r to the first times, we took the derivative of the radius with respect to time. So that's f prime times s is going to be h. Ooh, this looks like it's going to be fun to plug in numbers. And then now we're going to take the derivative of h, but that's going to be 1 times dh dt. I think I'm going to name my kid DHDT. If I have another kid, I'm going to name my kid DHDT. That's kind of a cool name. And then times f, which is going to be another pi r squared. And oh man, let's plug stuff in, man. We look at all this stuff we could plug in. Oh, I'm so excited. I'm so excited. I just can't hide it. Okay, so dv dt looks like it's about 4 pi. And I'm messing up the colors now. Equals pi times 2 times 3 times 2 times 3 times the rate of the radius, which is 2 centimeters, so 2, times the height, which was 4, plus 1 times dh dt, and we don't know what that is, times pi, times the radius, which was 3, squared. Ooh. And now let's do some magic. 2 times 3 times 2 times 4 is boop, 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 48 pi. Okay, so we got 48 pi over here. We got plus this 3 squared is 9, so we got 9 pi here times dh dt, the name of my next child. And let's go and divide that minus that 48 pi over. 4 pi minus 48 pi is going to be a negative 44 pi equals 9 pi dh dt. And I think I have a mistake. Nope, I don't think I have a mistake, but I think I have a mistake. 9 pi dh dt. And now let's go and divide this over. And we got negative 44 over 9. And negative 44 over 9, if we do this on the calculator, is going to be 4.889, which is the answer. I thought it did things wrong because when we're filling up a cylinder, I should expect the height to actually be increasing, the rate of the height to be increasing, but the way they wrote the problem, it looks like the height is decreasing, which is kind of weird, but that's what the answer is. I think it's just not a very well written problem. That's the most work that you'll have to do for a problem. I would recommend rewatching any parts that you had any questions about, and I will see you in class. Thank you.